Okay, so before the break, we brought out what is our dz and dy. Two method of calculation. The forces are the same. So again, we do exactly like what we have done earlier. We're going to calculate. We're going to identify what is our torque and things like that. Okay. So the first thing we're going to do, we're going to draw in different planes. Okay. So we are going to look at the XY plane now. Okay. So I'm going to make this smaller. Right. So we are going to now sketch our what we are viewing at. So we are going to view this is our X, this is our Y, rotation about Z. Okay, so I'm going to sketch okay, and then the one the other direction. Okay. Right. So we are aware that we have a force coming down here. And this is our dy, which is 12 times 10 to the power 3. And then we have another force, dz. Okay. And is going in at 5,000 or 5 times 10 to the power 3. All right. So again, we draw our element. Right. Then we draw our centroid or geometric axis. Okay. Right. So now you can see the 12. So ignore the cross and the dots. Okay. So just view at the complete arrow. So we know that there's a perpendicular distance here. Right. We are aware of this. And then this perpendicular distance that we can see over here. This is 0.15 meter. And the perpendicular distance, the applied force is parallel to the what? To the axis, right? So we are going to take it to the centroid. And we know that this will induce a moment about Z in this way. So over here is in compression. Down here is in what? Tensile. Right. So already now you can see that you can calculate MZ. Right. So MZ is equal to 12 times 10 to the power 3. Right. Is equal to right, and we declare there's only one, so if this is positive, okay, and then multiply by a perpendicular distance of 0.15. Okay, so 12 power 3 multiplied by 1.5 is equal to 1,800. I think this is in Newton meter. Yep, Newton meter. And then we know that we're going to put in the formula where it's now we are calculating based on stress Y. Okay. So whether it's stress Y X, stress X, if this if your geometric axis is parallel to the Y axis, you are calculating stress Y. Okay. So this will be equal to using the formula mz over izz multiplied by a distance x. we know that element H will have compression, right? Because it's compression, right? So negative. Did I write negative or positive earlier? I can't remember now. What did I write? Yeah, positive and negative, right? So we know that it's going to go through compression. So now you see anything else to look from this point of view? The answer is no. Okay, so we again view it from a different point of view now. So now I'm going to change the point of view to we're going to view in the YZ orientation. Okay, so now this is my Y. And then we have our Z. And then we know that this is rotation about X. Okay, so now when we sketch this out, okay, so I'm going to use the same height over here. Oops, sorry. Right. And then I'm going to draw a circle. Right. Then we're going to locate our element H. And then we are going to draw our geometric axis relative to the element. Wrong color. And then we're going to put in our forces. So we have our 12 times 10 to the power 3. And that 12 times 10 to the power 3, you can see is aligned to the what? Is aligned to the geometric axis, right? So you guys know what that means, right? And then we have over here, we have 5 times 10 to the power 3. Okay. So from here, we know that we can immediately identify that we have a PY. Okay. So PY we know that we have a PY is equal to 12 times 10 to the power 3 Newton. And then so this one, we know that it's going to generate stress in the Y direction. So this is PY over A. A is the cross-sectional area. So this will be also equal to PY of your element H. Okay. Now, then we have our VZ. Okay. So we have our VZ. So positive is going in this direction. So the VZ is equal to 5 times 10 to the power 3 Newton. Okay. Because the 5 times 10 to the power 3 will also act will induce a shear force 5 to the 10 power 3 Newton element H. Now, the 5 times 10 to the power 3 is perpendicular to the centroid. So it's going to induce a moment, right? And then now the distance is to the element. So we know that the distance from here to here, right? We know that the distance from here to here is equal to what? Is equal to, 300, 200. So 0.2 meters. So from here, we can immediately declare that we are going to have, I'm going to choose this side as positive, right? So this is going to be moment about X, right? Moment about X axis. So 5 times 10 to the power 3 multiplied by a distance of 0.2. So this will be equal to 5 power 3 times 5.2. Okay, so it's going to be equal to 1,000 Newton meter. So, but the thing is, now our stress Y, we know that it's going to mx over Ixx multiplied by Y, right? So for element H, right, is equal to 0. This is because of Y is equal to 0, right? Because element H is at the geometric axis. Okay. So, but we still have to calculate. We don't know initially. Okay. Right. Anything else to do? The 12 will induce a axial load. The 5,000 will induce a shear force. Okay, and then will induce a moment, and then on element H we found it is equal to 0. Okay, so nothing else to do. We will go to the third view. Okay, so now we are going to do the third view, the plan view. I mean, throughout my years of teaching, I find like this is the easiest way in terms that you will make less mistake, especially identifying moments, torque. Okay, I'm showing the last view, and you're like, oh, we have another force coming. Okay, so then the or another type of load coming. So we are going to now view on. So now this is our Z, and this is our X, and this is rotation by Y. Okay, so if I view from here, it's going to look like that. Again, this is just a sketch. Right? This is just a sketch. And then I have either detail. And then from here, we have our element H. And then we draw our geometric axis relative to the element. Okay. And then down here, from this view, we have a force going down by 12 times 10 to the power 3 Newton. Okay. And then we have another load coming this side at 5,000 Newton. And now you realize that, hey, right? If you look at this, if the structure were to deform due to the load, it will look something like that, right? And this is now where your 5,000 Newton is. And you realize that the green dot, right? The green dot did not move at all. The green dot is still a green dot. Okay, so when there's a case, we know that we are having a torque. Okay, so when this is the case, we are aware that we have a torque about the x-axis, the y-axis, I do apologize. So now this will be equal to 5,000 multiplied by a distance of 0.15. So 5,000 multiplied by 0.15 is equal to 750 Newton meter. Okay, so this is how you identify whether it's a torque or a moment, right? So then from here, you know that the shear is equal to TR or TY R over J, and you know that the shear at point H will not be equal to 0. Okay. So let me sketch the deformation pattern due to 5 times 10 to the power 3. So 5 times 10 to the power 3, the deformation will look like this. Right. So we have a moment about Z. Sorry, about X. And then again, we have compression on one side, tensile on the other side. And likewise over here, yeah, so the deformation pattern that we get for this, the deformation pattern will look like this. Okay, because of the right. So you can see the moment will induce a different type of deformation pattern relative to the what? Relative to the torque. Okay, so as I said, there are some departments in mechanical or in the faculty of engineering that specify that torque and moment are the same. Nope, they are as different as it comes. As you can see, okay, I'm going to now pick something that is not cylindrical, round. Okay, we're going to pick a rectangular structure now. Okay, so I'm going to pick this structure over here. Initially, it looks like really like difficult, but it's actually not. Okay, you look at this, right? So we have two elements of interest now, right? We have element A and we have element B. Okay, so given to us,